So first of all, I'm sorry that the seminar was delayed last week, and let's start with the new part from this week. So thanks, Kwang.
All right, so let me try to share my screen now, because right now my PC is back on the play, so I use the method I tried last time. So hopefully, can we now see my screen now? Okay, so this is shared from my tablet. All right, so we'll continue our talk today. So today mainly I'm going to introduce the Markov process and strong Markov process. Okay, so use the materials we defined last time, and today we're going to continue. All right, so let's start with a concept which is called the conditional expectation. Okay, so I'm going to add the line first. All right, so we start with our definition. Oops. So I just woke up. It's a bit hard for me to write. I apologize if my writing is extremely ugly at this time. Well, so the conditional expectation is very useful in terms of theoretical computation. Okay, so we all remember in the elementary probability, we've learned something called conditional probability. And this is the generalization of that. Okay, right. So let's say we have a random variable, so RV for short. So on a certain probability space, all right, so from our discussion last time, I really do not need to specify this space because we can always choose what we want. Okay. And we'd assume that this random variable is integrable, meaning the expectation of x less than positive infinity. All right, so for people who's not familiar with this notation, this one really means we're taking the integral with respect to the probability measure. Okay, that's the definition of expectation. Okay. All right. So so that's why I said we want it to be integral. Okay, this is the same thing. All right. So and then under this condition, we will choose a certain sub-sigma field or sub-sigma algebra. So no G. Sigma algebra. And then there will be a unique random variable, which will use this notation, which is very important in today's talk. I'll write it as expectation of x given g. Okay. So here, the bar here means given a certain condition or a condition on a certain information, stream of information. Well, so we have two properties for this definition, or two requirements for this definition. The first one, which is extremely important because sometimes people overlook the first one. Right. So this conditional expectation condition on sigma algebra G has to be G measurable. Okay, that's the first one. Has to be G measurable. And the second one, which is the defining property, says for any set, oops. we must have. Okay, right. So this equation, if we use, well, this is nice, right? Because that's what appears in most of the textbooks. But what I prefer is to write this equivalent form. This one is just a characteristic function. Okay, like this. Well, if we use the expectation notation, then this one simply means so these are equivalent. This is equivalent to. Okay. Well, so now you can see from the last equation, you can see why do we call this random variable the conditional expectation. So this characteristic function or indicator function is usually how we realize a string of information. Because remember, this A has to be from this sigma algebra G. Okay. So when we put this A here and taking the expectation, these two, we cannot distinguish these two because the expectation under, sort of like under the information of G, the expectation of these two, they're always the same. Okay, so that's why we say this is the conditional expectation. Okay, so well, if this is the first time you've seen this definition, I would suggest you just use your intuition. Conditional is just like the intuition for the conditional probability. Okay, because they are just the same thing. It's just here we're using the language of magic theory to describe this one. Okay, and as you can see, as a direct consequence, I can change this to any random variable z, which is measurable, which is g measurable. This has to be 0. Because for the defining property here is the indicator function. And then indicator function will give us simple functions. And simple function can approximate any bounded measurable function. Okay, so here we just assume z is bounded and g measurable, then this condition is still true. Okay, all right, so this is the conditional expectation. And now we're going to introduce another notation, which is the conditional probability, right? So let's say we have an event. So
Can I ask you a quick question?
Yeah, sure.
So I have 2 questions. Is omega part of the sigma algebra G? Like, does G contain the omega, the whole set? Or doesn't matter?
Yeah, I'm sorry. So oops. Sorry, I have to reconnect my Okay, sorry, seems like I was having some internet issue. So I apologize. Can you repeat your question?
Oh yeah. So
right.
So you said that G is a sub-sigma algebra, and like,
yes,
is it any kind of sigma algebra, or does it contain omega, the whole set, as its element?
Well, any sigma algebra must contain the whole set omega, but it is a sub-sigma algebra of F. So here we do have a sigma algebra here, and this is the one equipped with the probability space, and we just take sub-sigma algebra of this one. But by definition, a sigma algebra has to contain omega as the one element.
Okay, and I have another question. So you named the random variable by expectation G, condition on G. like expectation
Uh,
X contingent on G, and is there a reason
Right.
that you're like we have a new random variable expectation X
Right.
that's slash
Conditional
G.
G. Right.
Yeah,
Conditional
yeah.
G.
So,
Yes. Mhm.
like, why do you define the random variable like that? Can you
Because
just
can I just what?
like can't you just
Mhm.
call it as a random variable Y or something? Like, why do you
Yes,
have to
of
use
course.
X?
You can call it whatever you want. But if we define this way, then the convention is to write it like this way. So there's no reason for me specifically writing it like this, but this is just the convention.
Okay.
Right. So does this answer your question? Okay. Right. Just return to your first point, because really this sub-sigma algebra G contains the entire set omega. So therefore, you can actually take this as one of the property, is that when we take in the expectation, they must be equal. Okay, this has to be the same as this one. Okay, because if we just use omega as the set from the sub-sigma algebra, then this is what we get, and this is true. Okay. Right. So let's continue. So let's say we have any event from F.
So just the one question or comment.
Yeah,
So
sure.
the conditional expectation should be L1 function, right?
Yes, I specified here it has to be L1.
I mean the conditional expectation, not the given random variable.
For this one, it's automatically in L1. This is by definition, because we always do this integration here. So yes, integrability is assumed.
Combined with Jensen, right? I got it.
Right. You can think of that way, but we do not use the strictly speaking, we do not use Jensen here. But yes, you can use that to prove it.
Because in my perspective, this is just a Radon Euclidean derivative. So without L1 condition, it seems a little bit awkward. So
this is a very good point. This is the density, and actually, right. So since you bring this one up, so just a quick remark. So this one is the density of this measure. So A has to be. Okay. Okay, they're the exact same thing, because this one defines a measure on the sub-sigma algebra G. And this one, because X is integrable with respect to P, so therefore it is absolutely continuous with respect to P. So we do have a density, and this density is exactly this one. And because we define this measured on G, so the density is automatically G measurable. Okay. So this one is exactly the density. But usually we do not use this property from the Radon-Nikodym theorem. What we use is this defining property, which is this one here. Okay, which is this one here. And that's what we usually do, because whenever I see an exercise on the conditional expectation, I always use this. Should be able to solve it. Okay, that's just my experience. Right? Okay. So now let's continue. So the important definition, another important definition for us today is the following. So let's say we have a certain event, let's say in F, and then the conditional probability of this event given a certain sigma algebra, sub-sigma algebra. This is defined to be so here, this one sub B is just to indicate the function of B. And here we use the conditional expectation we just defined earlier. Okay, and you can check if this sigma algebra, you can change everything to you can change this sigma algebra to a single set or a single event. Okay, just by exactly the same thing, just change it to the single event, and you can check this definition coincides with the elementary definition which we study in our undergrads, the conditional probability. Okay, so therefore, what I've done here is just the generalization. Okay, using the measure theory language to generalize what we have learned before. Okay, all right. So that's a very short introduction to the conditional expectation because we need this concept to define the Markov process. Okay, right. So whenever you have questions, we can always come back because this is not that straightforward, to be honest. Right. So now I can give my definition. Right. So let's say we have adapted and d-dimensional process. So I'll use xt, ft, which is the filtration. Okay. And recall that adaptive means for any t, xt is ft measurable. And on a certain probability space, I'm going to specify which one it is. Starting at a certain point, x is 0. So now we do have two conditions. Well, the first one is very intuitive because we want to specify the starting point. So x0 has to be x0. Okay. This probability has to be 1. And the second one, which is the most important one, for any st and any set from the Borel sigma algebra of Rt, the probability of here. All right. So now let me explain. For condition number 1, this is just the intuition. We just want to specify the starting point. And for the general definition, we can actually put a starting distribution here, meaning instead of a point, we'll have a measure. And the law of x0 is that given measure. Okay, so that's very easy to generalize. But here, the important thing is the second part, right? So the second part says, if we want to look into the future, that's s plus t, and given a certain information, that's the filtration up to time s, and then the only useful part of this information is the endpoint xs, okay? Because the historical data before time s, they are irrelevant when we're trying to predict, for example, predict the future or something. So let me draw a graph here. So this is the time. Use t here. Yeah, this is the point s. This is the point s plus t. Okay, and we want to study this distribution of the process at this time. Okay, want to study the distribution, and we observe this process up to time s. Let's say it's like this. Okay, so we're given this information, and we want to potentially study the distribution of the process at time s plus t. Okay, study the distribution, and the only useful information is this single point. It's this single point. Okay, we don't have to look at the historical data before this point. The only useful information is this single point. Okay, is that clear? All right. So in other words, although I did not put in the definition, in other words, we can always restart the process. Okay, we can always restart the process at this point. Okay, and then I restart this process. Then this one can be taken as a brand new process. So after this point, this one can be taken as a brand new Markov process with the starting point, which is this point here. Okay. All right, and you can actually rigorously prove this just by using this definition. Okay, you can prove this. All right. So let me see here. Okay. So with this one, I'm going to first prove that the Brownian motion, which I introduced last time, is a Markov process. Okay. It's not that straightforward. Okay. Although intuitively it is obvious, but to actually prove it using this definition, it's not that straightforward. Okay. All right. So, example. So I'll say three-dimensional Brownian motion is Markov. Okay, I'm going to prove this one. So our goal is to prove so an A is just any Borel set from RD. Our goal is to prove this. All right. And whenever we see Brownian motion and we see, we always wanted to use the increment. So therefore, we have right for the first conditional probability, I just plus and minus BS to get the first term, which I just wrote here. All right, and now I need to prove a result. Just claim here. Okay, and I claim given provided that X and Y are independent. Oops. X and are independent. And so if X and this sigma field or sigma algebra G, they are independent, and also Y is G measurable, then I claim this equation is true. Okay, and you can see that this is actually relevant to our case because in our case, this BS is going to be Fs measurable, right? Because by definition, Fs is just the sigma, is just the filtration generated by Bs up to time s. And by the defining property of Brownian motion, this increment is independent from Fs. Okay, so therefore this claim is really related to our case. Right? To prove this result, we're going to use. I'm sorry. So I did not specify A and B. So A cross B is just a rectangle in RD squared. I'm sorry. I still have steam here. Okay, so A cross B is just any rectangle in RD. So meaning they are just a product of intervals. Okay, right. So I prove this first. So to prove this one, we're going to use the definition of conditional probability. This is just the expectation of right? This is just the definition of conditional probability. Right? And now we're going to use a very important property of conditional probability is that if a certain random variable is G measurable, then we can take it out of the conditional probability or conditional expectation. So here in this case, because Y is G measurable, okay, right here. So therefore, this random variable is actually G measurable. So therefore, we can take this one out of the conditional expectation. Okay. This is the property of conditional expectation. And then the next step, the crucial step, is to use the independence between X and G. Okay. So whenever you are conditioned a certain random variable, to something which it is independent from, then this one coincides with the usual expectation. Okay, so we can throw away this G here. All right. So now we have done the computations here for this term, for the starting term here, for this term here. Okay. And now let's try to compute the second one, which is the one here, Okay. And we will see it's actually we will end up with the same result. Okay. And now because as before, this variable is actually measurable with respect to the sigma algebra generated by y. So therefore, we can take it out, right? Therefore, we can take it out. Okay. And final step, the independence. Okay. So therefore, we'll get exactly this one. Okay. So therefore, we finished the proof for any set A cross B, okay, for any rectangle. And then if you have studied measure theory before, the next step is to argue that because the rectangle form a pi system or Duncan system, okay, so therefore any set that satisfies this condition or order set that satisfies this condition contains this pi system. So therefore it contains the sigma algebra generated by it. Okay. So therefore for any measurable set in RD or RD cross RD, we have this formula here, this equation here. And then our result, which is what we wanted to prove later, is to use this set this one is also measurable, right? It's also measurable in RD cross RD. So therefore, if we use this one to our previous result, so we just proved okay. So we just prove this for any measurable set in RD, A in RD. This must be true. Okay. All right. So now we're going to use our claim, apply this to this equation here, to this term here. To this term here, because BS is Fs measurable, BS plus T minus BS is independent from Fs. Okay, and because A is just any Borel set in RD, so therefore this one, by using our claim, this one is just the same as okay, by using our claim. And this finished proof of the Markov property of Brownian. Okay. Right, so it is not that straightforward, but still we will manage to get it. And now you can see why I emphasized at the beginning of last talk. Actually the more advanced theory of probability always relies on measure theory. Okay, because you can see actually this proof is entirely measure theory. Okay, there's nothing else. Okay, any questions so far? Okay, we're good. All right.
So we didn't. I totally understood what you did, but
Yeah.
in fact we rely on the fact that our semigroup is indeed so nice, right? So I cannot see, I mean, intuitively that the semigroup argument should be rely on this stuff. So it seems.
Well, so here what I prove is just a Markov property.
Mm-hmm.
So so this is of course this is the this is the step before we go into actually the application of the semigroup, right? So therefore it is, I think it is natural to not see anything related to the semigroup at this point, because this result is sort of like the prerequisite for us to define the semigroup. So
I see.
therefore here we must not use any semigroup things when we're doing something. That must be the step before the semigroup.
Okay, so at this point, we just use the definition of the Brownian motion, and that's it.
Right,
At this point.
right. That's what we have to do, because otherwise it is tautology. We're using
see.
something to prove something, so we cannot do that. Right.
Yeah, thanks.
Mhm. Right. So that's the Markov property. But this is not good enough, actually. This is not good enough because as you can see here in the definition, here this S and T, they are all fixed constants, right? S and T. And in a lot of real applications, okay, so let me draw another picture. In a lot of real applications, usually people are not satisfied to, for example, to observe the process up to a certain fixed time. We always set up a criteria so that when we observe something happened, we need to react to it, right? For example, and this is a very classical example. Let's say we have a set here. I'll call it A. And I want to do something when this process hit this set A. This is very reasonable, right? Because, for example, if you are working in the financial industry, you always want to sell a certain stock when it hits a certain price, right? So this is sort of like this. But as you can see, this time could be random, because it could be like this, or it could be like this, circling around and then hit this set. Okay, so therefore this Markov property is not good enough for us, because S and T here, they're all fixed numbers. Okay, so therefore very naturally we will want to generalize this result to random time, okay, to random times. And this is our definition for the strong Markov property, or the strong Markov process. And before that, a little bit more measure theory I have to introduce. So let's say, so we define T from omega to 0 to positive infinity. And we say this one is a stopping time with respect to a certain filtration Ft if okay. So this one is random. So T is from this probability space to presumably a positive number. And it is random because it is a function defined on omega. But this random time cannot be anything. We have to specify something. And therefore, we put this measurability assumption that the event that T is no more than T, a big T is no more than small t, is in this filtration f of T. Okay. Meaning, if you observe if this filtration is generated by a process, this is T. Then if you observe this process up to time T, you know if T is smaller or is no more than T or is bigger than T. Okay, that's the intuition. That is, if you observe this process up to a certain time T, you know if this stopping time had happened or not. Okay, something like this. All right, so this is very abstract. I'll now give you two examples so that you can understand what actually we're doing here. Because right now these things are extremely abstract, and the first time I saw this, the first time I studied this a few years ago, it just seems purely magic to me, because I really don't know what's going on. Okay. So I'll give you two examples. So once you can remember these two, so you know everything about the stopping time. Okay. example number 1. So assume xt is right continuous. I'll just write C0 for short. And A is open in RD. It's just any open set. And we define TA to be the infimum okay. So really this is the hidden time of the set A. Okay, because I'm taking the infimum. Okay, this is the hidden time of this set A. Okay. Then I can prove this. Well, so probably you have already realized that this is not the same as the definition here. Okay, but this is not a big difference because when we actually do some more analysis on this, we're going to assume this filtration is right continuous. And if the filtration is right continuous, then these two concepts, they coincide. Okay, so therefore there's no much difference here. But I just wanted to show you that if it is open, then we can prove this. Okay, and how do we do that? This is just one step proof. So TA is less than T. This is same as okay, so Q are the rational functions. Because here, I'm sorry, rational numbers, not functions. Because here we do have continuity assumption, right continuity, and that is enough for us. Because we can always approximate a certain point from the right using the rational numbers. So therefore, TA less than T is equivalent to this union, all rational numbers less than T, such that XS is inside this open set. Do you believe me? Do you believe me? Because for open set, if this process enters this open set, then we must be able to find a neighborhood of that point which contains in this open set. And then by continuity, we go to the left a little bit, then we must find a rational number such that XS is also in this open set, right? Right. So if you're having trouble to believe this equation, then you can actually try to rigorously prove this. Okay. So this one is actually correct. Right. So now with this, then as we can see, the right-hand side is just well, and because right, because XS in A is in the filtration up to time S, okay, and because filtration is increasing, so automatically it is in FT. Okay. And then we're taking a countable union because rational numbers, they're countable. So therefore, we're taking a countable union. So therefore, we must have.
So what if we replace the open set by the closed set? Then the argument
Right.
might
That's my next example. That's my next example. Okay. Very good question. Okay. So therefore, for open set, we have this result. Okay. For open set, this result. It's very straightforward. Just one step. Right. And then just like He pointed out, our next example is the closed set. Let's assume A is closed. And I'm going to show that okay. So as you can see here, if A is closed, then TA is the stopping time, because here is less or equal than. Okay. For open set, I only use strictly less. Okay. But for closed set, we can actually do less or equal. Right. So in other words, if A is closed, then the first hidden time of a closed set is the stopping time. Okay. Right. So to prove this, so actually so once I did the first step, then you can see what I'm heading to. Okay. So I'll define a sequence of sets to be the following. Okay. And so once you see this definition, you know where I'm heading now, right? Because now with this definition, A and they are open sets, and they all contain A. Okay. So basically, I just fix the closed set, and then I just look at the neighborhoods of this set. Okay, and this neighborhood gets finer and finer when n gets larger. Okay. And then I claim TA less or equal than T. Oh, so here xt has to be continuous. Okay. Not just right continuous, it has to be continuous from both sides. We cannot have jumps, because for closed set, it might jump inside the closed set. Okay. All right, so we assume this. And the intuition is as follows. So let's say we have a closed set, and we do have a neighborhood, open set around it. Then if this process reaches this closed set, then first it must reaches the open set, the neighborhood. Okay. So therefore I have this claim here. Okay. And then our result follows directly from this claim here. And you can prove this is just a topology proof. Okay. Just a topology proof. If this process hits this closed set inside this open set, and because this process is continuous, it cannot jump, then this process must first travel through the neighborhood and then inside this closed set. Okay. And therefore, this is seen FT by using our results from example 1. Okay. Right. So actually, to quote one of the professor, I learned the stochastic process from him. He said he's been studying stochastic processes for more than 20 years, and this is the only type of stopping time he's ever seen. It's always this. It's just maybe some a small variant of this, but it's always the hidden time that people will be using when we're dealing with the stopping time. Okay. All right. So continue. You want to ask something?
Yeah. So in fact, I'm trying to imagine what if we consider the Borel set as a generalization. It seems hard to say.
Well, so right. So that's why I did not go to Borel set, because I don't think we can actually do that, because usually most of the time we'll content ourselves with closed set. We always like working with the first heating time, time we reach a certain level or something. So probably you can try to prove for real set, maybe with some restrictions, but
might be hard to rigorously prove.
Right, yeah. Right. It might be well, it might be hard to get to a certain level of generality, I think, because for real sets, there can be some strange for real sets, right?
Right.
So
right.
it might not be hard, right?
Yeah, thank you.
But the closed set and open set are more than enough for most of the purposes. Okay. Right. Okay. Right. So we went a little bit slow today because I prepared a lot more, but it seems like I just have a few minutes left. So let me just give the definition of strong Markov process, and then maybe briefly introduce the intuition of what I wanted to talk. Right. So now, strong Markov process. So again, first one is trivial. Okay. Second one, the important part. Right. So here, so pay attention. I'm talking about stopping time. Then we have any t bigger than 0. Okay. So here, as you can see, the difference between strong Markov and Markov is just here. We allow random time. Okay. We allow random time. But this random type cannot be anything. Okay. It has to be stopping time. And like I said before, in the future, we're going to assume that ft is right continuous. Then we can actually use optional time or stopping time. So that means you can take off the equal. Okay, it could be strictly less or equal than something. Okay, but as you can see here, we did greatly generalize the Markov property by allowing random time. Okay, right. So my time is almost up. So I'll just briefly give you an intuition. So what I'm going to do next is the so-called refraction principle of Brownian motion. So I know Gunti is interested in this one, but sorry, today I will not have time to talk about this. Okay, but I can give you the intuition. Right. The intuition. So let's say we have a Brownian motion. So Brownian motion is a strong Markov process. Okay? And so it starts at 0.0, and we set up a certain level. Let's say B here. Okay, and let's just let this Brownian motion run. And when it first hits this level B, and because B as a single set in R is closed, right? So therefore, TB is going to be a stopping time. Okay, TB is going to be a stopping time. So therefore, we can, so once it hits this level B, then we can restart this process. And strong Markov process says we can always restart at stopping time. So therefore, if we ignore this part and let the Brownian motion restart when it first hits B, then this one is a new Brownian motion. And it is independent from the historical trajectory. Okay, right? So the significance of this property is that we can construct a coupling. Okay, so meaning if this is B and this is 2B, we can start a Brownian motion here, and then we reflect this one across this line B. Then we must have another one that's symmetrical about this B. And when they hit this process, we require they stick together. Okay, so once they hit this point, and by the strong Markov property, these two trajectories, they are Brownian motions. Okay, these are two Brownian motions. So we do not lose anything by requiring they stick together after they hit the time B. Okay, so that's where this, because the strong Markov property will allow to construct a coupling using this method. Okay, but historically, the refraction principle meant something else. So I mentioned this coupling because this is actually the original motivation for these talks. So I just briefly mentioned here, right? So the historical version of the refraction principle is as follows. Less than t. Okay, meaning the Brownian motion would hit level B before time t. Okay, Brownian motion would hit level B before time t. This one is the same as 2 times okay. So t is the ending time. So let me draw another picture. So let's say this is t. This is level B. Okay. So now if this Brownian motion hits level B before time t, then use the intuition introduced before. Then we may have a path like this, but because starting from this point, okay, everything after this point is a new Brownian motion. So therefore, just from the symmetrical property of Brownian motion, then we can imagine there's a shadow path. It goes like this, okay, which is symmetrical to the real one. And these two paths, they sort of like the same probability, because starting from this point, everything after this point is a new Brownian motion. So therefore, goes up, goes down, they must be the same, right? Okay, so therefore we use this argument. We must have okay. We must have these, right? Bigger than B, less than B, they must be the same. Because if we condition on the stopping time TB, everything after that red dot is a new Brownian motion. So it has it has equal chance to go up or down. So therefore, bigger than B or less than B has to be the same, because now the starting point is B, right? Okay. So now if I erase this one, add them up, this is exactly probability that TB is less than T. Okay. And of course, you can add something like this equal here, but it doesn't matter because the Brownian path is continuous. Okay. All right, and because just using the reflection principle, these two terms here, they're the same. So we must have This is probability 2, probability TB less than B, BT bigger than B. Okay. And the last step, BT bigger than B implies TB less than T. So at time T, BT is bigger than B, and because B is continuous, then it must cross the line B, the level B at some time before time T, right? So maybe I went a little bit too fast now. So now this is time T, and we know at time T, BT is above this line B. And because it is continuous, then it must cross this line at some point, right? Because it is continuous. There's no way you can get to a level above B without hitting the level B, right? So what I just said is that BT bigger than B implies TB less than T. Okay. Okay. In other words, this one is a subset. Okay, it's a subset. So therefore, if a subset intersects with the bigger set, then it's going to be the smaller set, right? Okay. Because this is the intersection of these two sets, and I just showed that this one is a subset of this one. So the intersection of these two must be the smallest. Okay. So therefore, we get this result here. This result here. Okay. So that's the refraction principle. Okay. And another significance or another consequence of this one is that we can compute the distribution of the supremum of the Brownian motion or infimum of the Brownian motion explicitly. Okay, we can actually write out these densities. Okay, so apologize for being extremely fast at the end. Okay, because I'm really running out of time. Okay, so next time I can give more details about this one and show you a few more examples with explicit computation, how we use this reflection principle and strong Markov property of Brownian motion. Okay. And maybe next time we can start talking about coupling, and then maybe in the future we can start talking about the martingale property of Brownian motion and a little bit more stochastic analysis. Okay, right. So that'll be all. Thank you. Thank you for your attention.
Okay, thank you.
Thank you.
So, is there any questions or comments?
I'm sorry, could you explain the last part where BT is larger than B is included in TB?
Okay, sure, right. So I also realized I was being extremely fast. So let's see, this is a level B, and this is time T. And the Brownian motion starts here. Okay. So TB less than T. So this event, this means the Brownian motion would hit B before time T, right? So there must be a collision somewhere here before time T. Okay. And then BT bigger than B means at this time, the Brownian motion is above level B. So let's say, for example, here, this is BT. Okay. And then because Brownian motion is continuous, it will not jump, right? So therefore, the trajectory from a point below B, which is B0, at time 0, to something above B, BT, then there must be some point in between that reaches level B, right? And this point has to be strictly less than T, right? So therefore, this event, BT bigger than B, really implies TB less than T, right? Does that make sense to you? Because for continuous process, if you go from below level B to up level B, then there must be a point in between where this process hits the level B, right? And it must be between these two endpoints. So therefore, we must be able to find a point bigger than 0, less than t, such that Bs is B. Okay, and this is enough for us to conclude that Tb is less than t. Okay, does that make sense?
So her network is not stable, so she's
okay.
apologized to.
Okay. Yeah, we can wait a little bit, but I just want to make sure I just explain myself. So I hope this explanation is it's sufficient for you to understand this.
Okay. Any other questions?
Just a quick question. Can you scroll up on your notes?
Okay, sure.
Look at the beginning of the example 1, and
Okay. Example 1, you're saying. Okay.
showing. So here. So in the definition of T sub A, you're saying that xt is an element of A, but
yes.
xt is a function, right? It's not.
Well, no.
Xt is a function that is.
So xt. So once you fix this time t, then xt is just an element in Rd.
But is there a
so x, right? X is a function, right? So x is a function that maps sort of like intuitively the time to Rd. So therefore, if we plug in a time t, this one is in Rd. This one is in Rd. So therefore, it makes sense to say a certain point in Rd is contained in an open set. Okay. So does that answer your question?
Yes.
Okay, great. Right. And then for example number 1, so it is crucial to have a continuity assumption. So here it is sufficient to have just one side continuity. Okay. All right.
Any other questions?
I have a quick question about the definition of the stopping time.
Okay, stopping time.
Yeah, so you define t to be a real valued function, so it does not take the value of infinity, but well, in the example you mentioned, well, the stopping time t is the infimum of a set, and well, if the set is an empty set, then well, typically it is defined to be an infinite value. So
so if the set is 0, if the set is empty set, I remember the convention is 0. I remember.
Okay.
Right. The convention is to set if a certain set is measured 0 set, then the hidden time of that one is 0. Yeah. Right. I think that's the convention. Just to avoid some nasty technical questions. So we set this convention, I think, right? Because well, I never recalled ever have to deal with such a situation. So I believe I can double check. I might be wrong. I can double check, but there's a convention for measure 0 sets, right?
Okay, thank you.
Right. Thank you.
Any other question? If not, we'll stop here to record, and we might have some informal chat if you want.